Okay, so the next chapter that we are jumping into, chapter 7, is all about applications of integration. So, looking at what we know how to find by using integration. And the first thing that should come to your mind when you think about an application of integration is area. So, 7.1 is focused on area between two or more curves. But I want to start, before we start talking about area between curves, of just reminding you how you found area under a curve. So, this question that you're looking at right here would be something that we would have done back in chapter 4 in Calc 1. So they give you a function. They want you to find the area under that curve starting at -1 and ending at 2. So if you write your definite integral, lower boundary -1, upper boundary 2, and you are integrating the function x squared plus 2x plus 5. Now, we did it a couple different ways. We did it by hand. So we have, when we integrate by hand, we do power 1 greater divide by that power, integrate every term individually here. And then we used the fundamental theorem of calculus, which said that we put the top boundary in first. So we put 2 in first, then we put -1 in, and then we subtract. There was also a way to do a definite integral on your calculator, and I want to remind you of this now because you're going to be using it a lot this chapter. Last chapter was very minimal as far as calculator usage. This chapter is the opposite. We're actually going to use it a ton. So to remind you how to do it on your calculator, let me just show you. You're going to go to Math button, and you're going to go to the 9th one down. You can scroll down to 9 if you want, or you can just hit the 9. I want to scroll down just once so you can see it. I went too far. The 9th one down says FNINT. I don't exactly know what it stands for, but in my mind, it's find numerical integral. It's going to set up the definite integral for you. You're going to put your boundaries in. So -1 is my lower boundary, 2 is my upper boundary. You're going to type your function, x squared plus 2x plus 5. You want to put what variable you're working with. I always say I'm working with X, even if it's T's or Y's or whatever. Just make sure whatever you type it in as, it matches that variable. And you hit enter, and it tells us that our answer is 21. So that's the area under the curve from -1 to 2 of that function. So looking at what we're doing today, so now we're looking at finding area between two curves. So some things to recall up above, and we just talked about it, so I don't really need to say much again. We're going to be using the fundamental theorem of calculus, which was what told us how to evaluate a definite integral, integrate, and then top boundary minus bottom boundary. And then the key calculator keys that we're going to use a lot is we're going to go to Math 9, which gives us FNINT, and it allows us to put that integral in and have the calculator basically do all the heavy lifting. So now if we're trying to find area between curves, so now instead of having a single curve, we have multiple curves. So I have things kind of color coded on the screen. So if we have these two curves, F is the blue kind of upside down parabola, G is the red parabola, and we want to find the area between them. If you think about it, and kind of color code a little bit, and we're going from A to B, if I just found the area under the blue curve, so let me make that in blue. So here would be my area in the blue, under the blue curve. But I don't want to include the area that's under the red curve because that's not part of the shaded region. So I'm going to subtract off the area under the red curve, and that would give me the area between the curves. So when we're finding area between curves, what you're going to often think of is looking at the functions, which curve is on top, which curve is on bottom, and we want to integrate it as the top curve minus the bottom curve. If you accidentally do it backwards, if you accidentally do bottom curve minus top curve, what it will do is it will negate your answer. So if your answer should have been 3.5, you would get something like a -3.5. Your boundaries of integration are going to be when the area starts and when the area stops. So we say it starts at A, ends at B. Again, you want to go from the smaller number to the bigger number when you're putting in your boundaries. So as we do go through problems now, I want to talk a little bit about the picture. And I'm going to have a lot of pictures available for you because I think having the picture there helps you see what's going on, and then talk about how we set it up. So here's an example. Here's all the boundaries. I'm kind of put it as a list off to the side. So we're looking at the area that is bounded by all of these different functions. You have x squared plus 2, which is a parabola, y equals x, which is a line that goes through the origin, x equals 0 and x equals 1 are your vertical boundaries vertical lines going from here to here, so from 0 to 1. And it creates this curve right here. When I set up my integral, I know I'm starting at 0 and ending at 1 because that's where my area is starting and stopping. My top curve, the curve that's on top, is the parabola, so it's going to be x squared plus 2 minus my bottom curve is just x. So this is my top curve. This is my bottom curve. I often label them T's and B's. Now, if you have to integrate it by hand, this one isn't awful to do by hand. You can go through and do it. If you are allowed to use a calculator, then by all means grab it. So you're going to go again, math 9, type in your boundaries 0 to 1, type in your function. You don't need parentheses here because there's nothing to distribute. So you can just type in x squared plus 2 minus x. You do have to put x as the variable you chose to work in. I personally like fractions way more than decimals. So if you get a decimal like this one, you're going to go to math, where it says fraction, the very first one. You're going to hit enter twice. And I get an answer of 11/6. So what this represents is it represents the area of that shaded region, the part that's in gray. Here's one where we have two functions. We have a parabola and a line. The parabola I drew in red, the x squared minus 4x minus 5. And then the line I drew in blue, the 2x minus 5. First thing we need to figure out is where this area starts and stops. Now, if you're allowed to use a calculator, you can use the calculator to find those intersections. Oftentimes with one like this where you can actually do it by hand. So if I want to know where the area starts and stops, it's going to be the intersection. So you're going to set this up as when does x squared minus 4x minus 5 equal 2x minus 5? And I'm going to get everything on one side. So I'm going to subtract 2x and add 5, subtract 2x and add 5. So we get x squared minus 6x equals 0. So if we factor out an x minus 6, that tells us that our intersection points are 0 and 6, which you can see from the graph. There's 0, there's 6. Oftentimes, if they don't let you use a calculator, they're going to ask you to set it up, including finding the boundaries, but they may not ask for a final answer. So with this, we're going to go from 0 to 6. My top curve, the curve that's on top of this gray region that bounds it on the above, would be the blue one, which is the line. So we're going to have 2x minus 5. Minus my bottom curve is x squared minus 4x minus 5. And then at this point, if you want to simplify, you can. If you want to say, nope, I'm done, I'm ready to go to my calculator, that's fine too. I have seen questions where they don't even want the final answer. They just want to see if you know how to set it up adequately. I actually like questions like that because it saves you some time. So I'm going to go to math 9. I'm going from 0 to 6. My top curve, I'm going to put in parentheses, is 2x minus 5. Minus my bottom curve, I'm going to put that in parentheses as well, is x squared minus 4x minus 5. And I am working in terms of x. And I get 36. And again, that is representing that shaded in area. Here's another one that's very similar. We have two curves. We have a parabola that's in red, the 2 minus x squared, and we have a line x that's in blue. If I want to see where they intersect, obviously I have a picture here, but it is nice to be able to do it without the aid of a picture. So if I set 2 minus x squared equal to x, I'm going to bring everything to the right side. So I'm going to add x squared here. I'm also going to subtract 2. If they don't let you use a calculator, this has to factor nicely. If they let you use a calculator, it probably means the x values aren't very pretty. So my intersections are at -2 and +1. -2 is where the area starts. +1 is where the area stops. So I'm going to set up my boundaries from -2 to 1. My top curve, what is on top of this gray shaded region, is the parabola. So it's going to be the 2 minus x squared. The bottom curve is the line x, so minus x, top minus bottom. And then again, I'm going to go to my calculator. I could do this one by hand. So if they didn't let me use a calculator, I could get by. The mental math would be a little frustrating, but I could do it. So I've got -2 to 1. And then I'm going to put my top minus bottom. So 2 minus x squared minus x. And then put my boundaries in. And I get 4.5, or you can write it as a fraction, 9/2. I don't care decimal or fraction. This one's a pretty clean decimal, so that's fine. So my options are 4.5 or 9/2. I want to show you one more. I want to show you what happens with trig. So what we know about trig functions, specifically sine and cosine, is they're very repetitive. They have a period that they repeat over and over again. With sine and cosine, every 2 pi it repeats. So you're never going to be given a trig one like this and just say find the area of what's enclosed, because it keeps enclosing a region after a region after a region. It's very repetitive. So what you'll see, one of two things. Either they will tell you where to start and stop, so they will give you the boundaries of integration, or they're going to say something like this, where it just says, I want the area of one of the regions, because I realize that I'm going to just continually enclose the same region over and over and over again. So there has to be some sort of extra information with trig because of how repetitive it is. So the next thing is it really helps to kind of have a picture and see what's going on here. So here you have a nice looking graph here. The red function is your sine graph, and then the blue function is your cosine graph. And I just isolated just the very first region that shows up on the positive side and saying, let's find the area of this. If we went further out, we would just have another region that's the same over and over again. So let's stick with the easiest. So now we have to figure out where my boundaries are. And this is going to come from when sine and cosine are equal to each other. Obviously, they're equal to each other over and over and over again, but I'm specifically looking for the first 2 times in the unit circle that they're equal to each other. So you might have to kind of sit back and think about what your unit circle looks like and go through and say, where are sine and cosine the same? Well, sine and cosine end up the same at pi over 4. So they both, at pi over 4, they're both equal to radical 2 over 2. And then again, in the third quadrant at 5 pi over 4, they are both equal to negative radical 2 over 2. So those are the 2 times, if you go around the unit circle, that you would see sine and cosine are equal. So those are going to be your boundaries. So again, the most challenging part of this one is probably the setup, just trying to figure out those boundaries with trig. Top minus bottom, in the picture that I'm looking at, that enclosed region, the top curve is the sine curve. The bottom curve is the cosine curve. Now, if you accidentally did this wrong, you would get a negative when you did it on your calculator. Now, when you are in your calculator, another thing, make sure you're in radian mode. My calculator never leaves radian mode, so I'm going to leave it. So math 9, I'm going to go from pi over 4 to 5 pi over 4. And then I'm going to type in my sine of x minus my cosine of x. And make sure I put it in terms of x. I should expect decimals here. And the reason I'm expecting decimals is because I'm working with trig functions and I'm working with boundaries that have pi in it. You always want to go out 3 places when you deal with decimals. So 2.828. This is you could do this in an exact form in terms of pi. That is possible. When you integrate sine, you integrate cosine. With a calculator is completely fine. Honestly, for most of these problems, I am the most concerned about your setup. I want to make sure that you can comfortably find your boundaries or use the boundaries that are given, and then you can set up what's my top curve, what's my bottom curve, and set up the integration. So that's a little introduction of how we find area between curves. Hopefully it relates a lot to what we did last year.